All right. Hi, everyone. Thanks for coming to the Graphs and Matroids seminar. Today we have Zishen Q, who's going to be talking about minimal induced subgraphs of two classes of two connected non-Hamiltonian graphs. He's a student at the University of Waterloo. Go ahead, Zishen.
Thank you, Shayla. Thanks for inviting me to give a talk at this seminar. So yeah, my name is Zishen Q, and most people call me Jason. And I'm going to give some background and then talk about the proofs in some joint work with Joseph Cherian, Sepir Hajibi, and Sophie Spurkle. And the paper is accepted to discrete mathematics, so it'll appear there soon. And the title is Minimal Induced Subgraphs of Two Classes of Two Connected Non-Hamiltonian Graphs. So first, I'll talk about the title. If you just ignore the two classes for a moment there, the title is Minimal Induced Subgraphs of Two Connected Non-Hamiltonian Graphs. So that implies that if you get a smaller induced subgraph that's still two connected, that it should be Hamiltonian. So in other words, these are sort of the minimal obstructions to Hamiltonicity in a two connected graph. Well, you obviously need two connected because if you have a cut vertex, it can't be Hamiltonian. Okay. I know that Hamiltonicity is not the most popular subject, so I'll remind you on some of the definitions here. So for a graph G, a Hamiltonian path is a path P of G such that the vertices of the path is the vertices of the entire graph. And a Hamiltonian cycle is a cycle C of G such that the vertices of the cycle is the vertices of the entire graph. And we call a graph Hamiltonian if there's a Hamiltonian cycle in G. Sometimes if you have a Hamiltonian path in the literature, they call it traceable, but that won't be too relevant because we'll mostly be focusing on the cycles here. Okay, so I've drawn some examples here. And on the left is what we call a two nova. And on the right, it's two triangles connected by three paths. So I've highlighted a Hamiltonian path in the two nova. And there's no Hamiltonian cycle there. If you, suppose there was a Hamiltonian cycle there, a potential one, then you look at the horizontal vertices, they're all degree 2. So any Hamiltonian cycle that contains them has to contain both their edges. And well, if you add all those edges into your graph, then you have degree 3 vertices on the top and bottom. So there's no Hamiltonian cycle that contains that. And I've constructed these, okay, so I've highlighted the Hamiltonian cycle in the right part as well. I've constructed these to be like a little, if you tweak them a tiny bit, then they'll fail the conditions. For the graph on the left, if you add a 2-edge path from the top to the bottom vertex, this is not really a natural thing to do, but just suppose that you did that. Then it wouldn't have a Hamiltonian path. Well, in a Hamiltonian path, only 2 of the vertices can be degree 1. And you have 4, if you added that 2-edge path from top to bottom, then you have 4 vertices that are degree 2. So 2 of them have to have both of the incident edges inside the path. And that gives you a cycle already. And there's no cycle in a path, so it can't have that. And in this right side, the 3 triangles attached by 3 paths, if you subdivided the center edge, then those paths all have degree 2 vertices. So you have to add an entire path into any potential Hamiltonian cycle. And then all you're left with is you have to have those paths in your potential Hamiltonian cycle, and you're left with 2 triangles. And you got to connect the ends of 3 paths on each side, which you can't do. So it's not if you added the subdivided, if you subdivided the edge in the center, it's not Hamiltonian. Okay, so the types of so the Hamiltonicity is obviously the focus of the paper, but the types of results that we want to talk about are more about induced subgraphs. You know, there's a lot of results on degrees and other types of structural conditions like planarity, along with other things, local connectedness. But the types of results we're interested in are where you just don't have an induced subgraph. If you exclude certain induced subgraphs and you give yourself global connectivity conditions, can you show that you're Hamiltonian? And the earliest result I could find of this type is this one by Goodman and Hedanimi in 1973. And they show that if G is a 2 connected graph and contains no induced subgraph isomorphic to either K13 or K13 with an additional edge, then G is Hamiltonian. So here's the proof. Suppose you know that G is 2 connected non-Hamiltonian. Then look at the largest cycle, C in G. It doesn't contain every single vertex. So there's a vertex that's adjacent to the cycle C that's not in the cycle. So call that vertex U, and it's adjacent to V on the cycle. And then we'll label the vertices before and after V in the cycle X and Y. Okay, so X and U can't have an edge. If they did, then we could have made the cycle longer. We just delete the edge XV and put in XU and UV. And the same argument holds for UY. So that also doesn't have an edge. So these dotted lines mean there cannot be an edge there. Now you have this structure. Just zoom in, take a look. We've actually determined all the pairs, whether or not they have edges or not, except for the pair XY. We know UX no edge, UY no edge. So if X and Y don't have an edge, then it's K13. If X and Y do have an edge, then it's K13 with an additional edge. So this proof is very nice. So, okay, about the diagrams in this talk. I don't like drawing diagrams in ticks when the diagrams are made just for proof. So the diagrams are a combination of hand-drawn diagrams, mouse-drawn diagrams, and tablet-drawn diagrams, because I don't have like consistent access to any of those three. Okay, so Goodman had Animi, the first result of this kind. And then there was Duffus, Gould, and Jacobson, who extended this result. They showed that, okay, so ignoring the first part for a second, if G is two connected and G does not contain a subgraph isomorphic to the claw or the net, the claw is just a K13 on the left here, and the net is the graph on the right here, then G is Hamiltonian. So this, if you just look at the two connected one, this is the extension of the previous result, because if you contain the net, then you contain the K13 plus an edge. And so I think they were more interested in the traceable in the Hamiltonian path here, but and I'll look at the result more from that sense for them. So these two induced subgraphs for the Hamiltonian path case are sort of minimal in a sense, and they're minimal in this sense. If you look at either of these graphs, just for example the claw, and you look at any connected induced subgraph, it's Hamiltonian. That sounds like a ridiculous statement, because the only thing you can do is like you can delete a vertex that's isolated, or a degree 1, or you can delete like all 3 vertices, and of course it's Hamiltonian because you're deleting almost the entire graph. There's so few vertices. But the same thing holds for the net. If you look at any connected induced subgraph, it's Hamiltonian. So in a sense, these two induced subgraphs are minimal obstructions to being traceable, minimal obstructions to being to containing a Hamiltonian path. So that's the sense that I want it to be minimal in. Okay. So okay, there's one other thing to say is that just because you're not okay, if you're Hamiltonian, if you're not Hamiltonian, it means you contain one of these. Sorry, if you're not, this is the traceable case. If you don't have a Hamiltonian path and you're connected, you contain one of these. But it doesn't work the other way around, right? You can always take like a complete graph and connect it to one of these induced subgraphs a few times and get a Hamiltonian path that contains one of these induced subgraphs. So it doesn't, just because you have those doesn't mean you're prevented from being traceable or Hamiltonian. Okay, so minimal obstructions to Hamiltonicity, and minimal obstructions to having a Hamiltonian path. So here are some definite, okay, so it's exactly what I just said before. Claw or net, if you look at every proper induced subgraph, it's either disconnected or contains a Hamiltonian path. So we call a graph H an HP obstruction if H is connected and has no Hamiltonian path, and every proper induced subgraph of H has a Hamiltonian path. So this is just what we said earlier. They're the minimal obstructions in the connected case. And by Duffus, Gould, and Jacobson, we actually know there's only 2 of these, and they're exactly the claw and the net. So we say that a graph H is a HC obstruction, Hamiltonian cycle obstruction, if H is 2 connected, has no Hamiltonian cycle, and every 2 connected proper induced subgraph of H has a Hamiltonian cycle. So we just swapped every instance of Hamiltonian path with Hamiltonian cycle, and we took connected and put 2 connected because that's what you need for Hamiltonian cycles. So this is a sort of a natural question to ask, but so the problem is this is actually not very easy. Okay, What's the strategy for trying to find these obstructions in the first place? Well, if you construct one, then you can just check the definition and show that it's an obstruction. To show that a graph is a minimum obstruction, just construct it and check the definition. You check that it's not, okay, I'll just do the HC one. HC obstructions, Hamiltonian cycle obstructions. If you construct a graph that you think is a HC obstruction, check that it has no Hamiltonian cycle, and then check that any two connected proper induced subgraph has a Hamiltonian cycle. And if you can prove those two things, then it's a minimum obstruction. Of course, the real question is to characterize all of them. And to do that, what you do is you just show that, well, I have a set S and I think that it's all of the minimal obstructions. Then, well, if G is two connected, okay, I wrote in the class to make it more general, but if G is two connected and it's S free, then it should just have a Hamiltonian cycle. So if you have any graph that has no Hamiltonian path cycle, it's going to contain one of these minimal obstructions in this sense. Okay, so here are some examples of HC obstructions. So as I said earlier, Duffus, School, and Jacobson, they resolved this problem for HP obstructions. They're just a claw in the net, two finite graphs, which is a very nice answer. So here's some HC obstructions. On the left, that's the net and a single universal vertex. So there's a triangle and three pendant vertices on the triangle. And I just put a universal vertex on it. And then here, this is a two nova. As I've shown before I've showed that it has a Hamiltonian path at least. And it also has no Hamiltonian cycle because of the degree 2 argument. And this is a theta, which is just you take two vertices and you put paths of length at least 2. So the edges are length 1 and then the squiggly lines are 1 or above paths. And then here is a triangle-free wheel. You need triangle-free because if you had a triangle, like you could just go around the rest of the wheel and then go into the center vertex and leave again. And that gives you a Hamiltonian cycle. But if you're triangle free, then you look at any one of the segments in between vertices that are adjacent to the center vertex, and they're degree 2. So you have to add in all those edges and you just get a cycle around the outside. But if these are all HC obstructions. If you look at any two connected induced subgraph for the okay, I won't do it for the snare because it's kind of complicated. For the two nova, you just have to delete one of the vertices, one of the degree 2 vertices or two of the degree 2 vertices. And then you just get a 4 cycle or a 3 cycle there. No, you don't actually get a 4 cycle. You get a 4 cycle plus an edge, but there is a 4 cycle, so it's good enough. For the theta, you have to delete basically an entire path. Like if you delete any degree 2 vertex and you don't delete the rest of the path, you're going to leave yourself with degree 1 vertices, so it's no longer two connected. And similar for the wheel, I guess you can delete the center vertex as well for the triangle-free wheel. But if you delete the segments, the degree 2 segments, you basically have to delete the entire segment as well. Okay, so we weren't actually able to find show that there's a set that's all the HC obstructions, but when you can't do it for, okay, wait, actually I started with more HC obstructions. I should talk about, okay, I forgot what my next slide was going to be. Here are some more HC obstructions, the more generalized than the two nova. So N sun is, you start with a cycle and 2 N vertices. And then you take all the even vertices, all vertices of even index, and you make a clique out of it. So in the two nova, it was a 4 cycle. So it's a 2 nova because it's 2 times 2 is 4, so it gives you a 4 cycle. And you take the even vertices and you make a clique. And then the last step is okay, so that's a 2 sun, and then the last step is you take a vertex and connect it to all the vertices in the clique. So as the 2 nova is exactly as constructed before, it's much simpler. But here's a 4 sun and 4 nova where you have a cycle of length 8, and there's 4 vertices in a clique, and the last, you add in a vertex that's connected to the entire clique. Okay, there's one more observation I wanted to make, which is that if you look at the N nova, it's a split graph. The clique plus a vertex that's connected to the entire clique is a clique, and then the rest of the degree 2 vertices don't have edges between one another, so they're a stable set. And same thing with the snare. It's actually the triangle and then the universal vertex forms the clique, and then the three outside vertices form the stable set. So these are both split graphs. So yeah, all n novae are HC obstructions. So what happens so we couldn't do it for all two connected graphs. So what happens when you can't do it for all of them? Well, you just do it for a specific class. So we tried to, we found some that were split graphs. So we did it for split graphs, and it sort of made sense. Okay, so a split graph is a graph where you can partition the vertices such that one of the sides of the partition is a stable set, no edges, and then the other set is a clique. So every pair has an edge. And we showed that if you have G, a two connected split graph with no induced subgraph isomorphic to the snare, or n nova for any n greater than or equal to 2, then G has a Hamiltonian cycle. So as I stated before, that this is the method of showing that these are all the HC obstructions. If you exclude them, then you get Hamiltonian. You're Hamiltonian, then that means that you got all of them. There's no left. Okay, so I'll try to show this, but yeah, I'll sketch the proof in all the steps of the proof, the claims. So we do this in 5 different claims. Okay, to set it up, you take G, SK, two connected split graph with no snare or n nova as induced subgraph, with K as large as possible. So the clique, there's no vertex in the stable set that's adjacent to all of the clique. That's all that means. So we proved this with 5 claims. So first, there's a vertex in the clique such that there's 3 neighbors in the stable set at least. Second, we show that if you have 2 vertices in the stable set that have 2 common neighbors in the clique, then their common neighbors are actually everything, the entire clique. And then we show that if you have the 3 neighbors, the 3 neighbors of your clique vertex that are distinct, you can characterize what their neighborhoods are like. In fact, if you look at all their neighborhoods, the intersection of all of them, it's just K. And if you look at the union of any 2 of them, it's all of the clique. And then we show that you can't actually have any degree higher than 3. The neighborhood of K in S is actually never higher than 3. So it's basically, there's going to be one of exactly 3, right? That's all that says. And lastly, we show that S only has 3 vertices. And after that, you can just draw a Hamiltonian cycle. So yeah, you end it with that. Okay. I know I wrote G equals SK, but I'm going to take the convention that I draw the K on the left. And here I've drawn these diagrams to show you some important graphs here and to try to get you used to this convention. The left side of these diagrams is actually just a clique. Even though I didn't draw any of the edges, they're all there. So the leftmost diagram, there's a triangle on the left side, and then it's connected to those 2 vertices on the stable set on the right in the prescribed way. So this is a 2 nova because, well, there's a 4 cycle there. If you go through the edges, just look at the top 4 vertices. There's a 4 cycle, and also the left 2 vertices are clique, and then you have a vertex in the bottom that connects to that clique. So that makes it a 2 nova by construction. This one's also a 2 nova, so that's the center one, because you just do the same thing. You get this 4 cycle, you get the clique, and you get a vertex, but this time in the stable set that connects the entire clique. It's just a different drawing of it. And I guess the problem is, like, the reason that these are drawn differently is because in the normal general version, there could be more vertices in the clique, and sometimes your 2 nova doesn't use a vertex in the clique. Okay, and on the right side is a snare. If you ignore the top vertex, the left 3 vertices, since they're in the clique, they form a triangle, and the triangle has 3 pendant vertices, and now all 6 of those vertices connect to the top vertex. So that's the snare. You have a net and you have a universal vertex. So that's what they look like as split graphs. All right, let's start on the 5 claims. So claim 1, there's a K and K with where the neighborhood intersect the stable set is at least 3. Well, okay, suppose not. then if you take all the vertices in S and just take 2 edges incident to each one of them and look at that graph, there's no degree 3. Well, okay, there's no 3 edges that are incident to at one vertex in K, because that's what the assumption was, that this didn't hold true. So there's only really two possibilities. There's like, you have some cycles, or you have just a paths, just some union of paths. So if it's a disjoint union of paths, each segment will look like the diagram drawn here on the left. And then you just connect the ends of the segments with the rest of the vertices in K, and you construct a cycle. So the other case is there's a cycle, which just means that, you know, you have this zigzag and then you go to S, and S goes to the first K again. But that's actually just an N-nova, because there's going to be an additional vertex in K, and that additional vertex in K plus that thing makes it N-nova. So that's just how you get the contradiction here. So there's at least a vertex. Well, that's just a sketch though, but there's at least a vertex K such that the neighborhood is at least 3 there. Okay. So now second claim, if you have 2 distinct vertices in S and their common neighborhood is at least size 2, then their common neighborhood is actually the entire clique. Well, suppose not, you know, like their common neighborhood is K prime here. And you have a K double prime that is not part of their common neighborhood. So you can basically, this is basically a 2 nova. There is actually another case, but this looks fine. So claim 3. If let K be in the clique and you pick 3 vertices in the neighborhood intersect the stable set, and they're going to be distinct. So we want to classify the neighborhoods. Okay, so if the intersections, so first we'll do the intersection is equal to K. If it's not equal to K, that means there's 2 vertices that have a common neighborhood of these 3 vertices in S. But this is just a 2 nova because, well, it's just what I drew before at the beginning, where you have these 4 vertices and 1 vertex on the right. Okay, so now you know that the first thing's true. Now, without loss of channeling, I say like K1 is adjacent to S1, K2 is adjacent to S2, K3 is adjacent to S3. They might not all be distinct. I'll just sort of gloss over that detail for now. So let's try to prove the second part. So here's, okay, so this diagram, if you just look at this and there are no other edges between the right and the left, then it's a snare. It's just what so, you know, the K1, K2, K3 make the triangle, S1, S2, S3 are pendant vertices, and K is the universal vertex to the net. So you're going to need to have some extra edges to make this not a snare. So like we'll just take S2, K1, because you could just pick any of them. They're just arbitrary labels. S2, K1 have more than 1 vertex as a common neighbor now. And in 2, we showed that if you have 2 vertices, in claim 2, we showed that if you have 2 vertices with more than 1 common neighbor, then their common neighborhood, the union of their neighborhoods is actually the entire thing. It's the entire clique. So, well, we need to include case, okay, so we've proven that for I, J equal to 1, 2. And if you look at just K3, it has to be adjacent to S1 or S2 because the neighborhood of S1 and S2 is all of K. So suppose that it's going to be S1. So I draw this edge, S1 to K3. Okay, well now S1 and S3 have a common neighborhood of size more than 1. So the union of their neighborhoods is also going to be just the entirety of K. So we've done it for 1, 3, I equals 1, J equals 3 as well. So we only need to do it for 2, 3. And if 2, 3 has a common neighborhood of size more than it, then you just do the same thing again. But suppose that it has the neighborhood, the shared neighborhood is only K. But then you notice that shared neighborhood of S1, S2 has to be entirely K. The shared neighborhood of S2 and S3 has to be an entire neighborhood of K. And the neighborhoods of S2 and S3 only intersect at K. So the neighborhood of S1 is just the entirety of K then, because it covers what S2 didn't cover that S3 covered, and it covers what S2 covered, but S3 didn't cover. And the only thing that both of those cover at once at the same time is K. So it covers everything except K by this argument. So S1 is just entirely of K, but that's you can't do that because we said that we made K as large as possible. So we should have moved S1 into K. Okay, the fourth claim. There's all the degrees of vertices in K intersect the stable set are going to be less than or equal to 3. Okay, so suppose not, suppose that there's a S4. Suppose that there's a S4 incident to K as well. Okay, and S4 is going to be incident to some K prime because the graph is 2 connected, so you need 2 edges. So K prime, if you look at it in relation to S1, S2, S3, it has to be incident to 2 of them. Because if it wasn't, say like it's not incident, say it's incident only to S1, then the union of the neighborhoods of S2 and S3 has to contain the entire clique. Wait, yeah, because we proved it here. So that's a contradiction. So it has to be 2 of them that are incident to this, so that the union of any 2 neighborhoods is the entire clique. So suppose that it's S2, S1, S2. But now you get these 2 edges, and if you just look at S1, S2, and S4, their intersection is more than 1 vertex, which was the first part of the claim 3. If you look at any 3 vertices, the intersection is just K. So here the intersection is K and K prime, which is a contradiction. I think this also makes a 2 nova, but I mean, the 2 nova comes up really often here. Okay, so that's claim 4. Now I have the first part. Okay, the claim 5 is just, we want to show that the set S is, has exactly 3 vertices. So suppose that the set S has 4 vertices. And I'm going to, okay, more than 3 vertices. And I'm going to take it so that 3 of these are incident to K. And S4 is down here somewhere. So in the first case, I'm going to have S4 incident to 2 vertices that are both not neighbors of a single SI. So say S1, like there's no edge between K prime and S1. There's no edge between K double prime and S1. But then it has to be incident to the other 2 vertices because of the same thing. The union of 2 neighborhoods have to be the whole clique. And if you just pick S1, S2, S2 has to be incident to both of these. If you pick S1, S3, then S3 has to be incident to both of these. So both of these have a neighborhood. And well, that gives you a 2 nova because you just do the same thing. Look at these, look at S2, S3, S4, K prime, K double prime. Okay, so what happens when you have 2 distinct neighbors which are both not incident to SI at the same time? So here, so suppose it's K1, K2. So S4 is incident to K1, it's incident to K2. And they're, okay, every it can't be the case that you're incident to all 3 of them at once because we showed that the intersection of S1, S2, and S3, the neighborhood of which is just K. So each one of these has to be not incident to something. So suppose that, K1 is not incident to S1, and suppose that K2 is not incident to S2. And neither of these can be K because that's how we chose S4. So assume that, okay, so we'll take K3 such that it's not adjacent to S3. So I should have drawn the dotted line here, but I guess I forgot to do it. So now if you look at S3, S4, K1, K2, K3, and there's no edge between K3 and S4, that's a 2 nova. It's the same beginning 2 nova. So that means there has to be that edge between K3 and S4. So S4, K3 is an edge here. And we can do the same thing for every single vertex that's not incident to S3. If you take any K3 equivalent not incident to S3 and you look at S3, S4, K1, K2, and K3 equivalent, that's going to form a 2 nova unless there's an edge from there to S4. And you can do this for any SI. You just, well, these are 3 non-edges. And if you just pick 2 of the K1, K2s, you can show that for any Ki that's not incident to Si, S4 is going to be incident to it. So this is, so what that means is, S4 is instant to all of these. But here, we showed that if you have two distinct neighbors, which are not neighbors of SI, then we obtain two nova. So it means there can only be one. So there's only one of K1, K2, K3. So this is actually the entire graph. And then okay, I should have just written down the Hamiltonian cycle get here, but so there's enough edges here that you get a Hamiltonian cycle. Okay, so S1 is not instant to K1, but it's actually instant to both of K2, K3. Like there's a lot of edges. It should be fine. I think, did I write it down somewhere? No, I didn't. Okay, so you just get a Hamiltonian cycle with these 8 vertices. This is actually just the entire graph, and I haven't drawn in some of the edges, but after you fill in the edges, it's just, you can just draw the Hamiltonian cycle. Okay, so now that we've proven all 5 of these claims, we can just show whatever's remaining. So this is, okay, so this is what the graph looks like. You have 3 vertices in S, and there's actually more of K, but we'll just pick some K2, K3, K1, such that K1 is not instant to S1, K2 is not instant to S2, and K3 is not instant to S3, which exists because they're not, you can't have it instant to the entire clique, or you'll have to move it, right? So if you just look at this exact graph, each K, it actually has to be instant to one more of the S's, since we showed that, we showed that it had to be K's for one of the claims. I can't remember which one now. So you get these red edges. The green edges just come from the choices, I guess. So if you take this graph and you just draw the path K, S1, K2, S3, K1, S2, and K3, and then you take, so there's a remainder of a clique here. You just make a Hamiltonian path in the clique that connects K3 to K, and then you just take those 2 paths, you join them together, and you get a Hamiltonian cycle. So with those 5 claims in this finite construction, you can obtain the theorem that you wanted, which is that split graphs, if you have a split graph, you have no N nova and no snare, and you're 2 connected, then you're Hamiltonian. Okay, so that's it for split graphs. So the paper is named 2 classes of 2 connected graphs. So what's the other class? And it's triangle-free graphs. And I feel like this result is not as interesting because it's actually possible to do better. But triangle-free is still pretty nice. So here's what it is for triangle-free. We showed that if G is 2 connected, triangle-free, contains no theta, closed theta, or triangle-free wheel, then G is Hamiltonian. And of course, that implies, as we said before, that thetas, triangle-free theta. Okay, no, it should be closed thetas. They're all triangle-free, but closed thetas and triangle-free wheels are all of the HC obstructions for triangle-free graphs. So the theta is just 2 vertices with 3 paths between them of length at least 2. And the triangle-free wheel is you have a cycle and you have a vertex that's you add a vertex that's adjacent to 3 vertices of the cycle, and there's no triangles. So the closed theta is that's the extra thing that we haven't seen, which is you just take the ends of the theta and you add an edge between them. So that's not really going to help you in obtaining a Hamiltonian cycle, because it's just an edge. And the way that you show that this is not Hamiltonian is you look at each vertex and each path, and you realize it's full of degree 2 vertices. So any potential Hamiltonian cycle has that in the entire path. And that same argument is still going to hold true because the ends are degree 3. So it's not going to help you to add another edge. Yeah, so just those 3 infinite classes will give you that, will give you the HC obstructions. So the proof of this, actually, we show that it's outer planar. So the first thing we show that is that, well, if you have a K4 minor, then you have one of those obstructions. Okay, so the G is triangle free, is 2 connected, and if it's a K4 minor, then it has one of those obstructions. And what you do here is you actually just you look at the K4 minor and you look at a model of it. So A1, A2, A3, and there's going to be A4, and these are going to be the components you contract to get your K4. And you're going to form a cycle, induced cycle from A1, A2, A3. And then I'm going to take an X in A4, and I'm going to take the shortest path to the cycle, which is within one of the components. So there's a P1 from X to A1, the shortest possible one that goes to the cycle. And there's a shortest path go from X4 to A3 and X4 to A2, and those are all paths. And then, you stop at the first vertex that's on the cycle. This is actually not that important. Like the only reason you do this is to show that there exists a path between two vertices on the cycle that are not adjacent. So if you look at the vertices that you attach to with those three paths, they're going to be like Y1, Y2, Y3, where Y1 is in A1 intersects C, Y2 is in A2 intersects C, Y3 is in A3 intersects C. And since it's not a triangle, two of those vertices are not going to be adjacent. And then the outside path just gives you a path between two non-adjacent vertices. That's all you really need from this part. So now you're just going to look at the cycle, and you know that there's a path that exists between two non-adjacent vertices of the cycle. And I'm just going to take the shortest such path, R, say. And this path doesn't give you a theta or induced or closed theta. And the only way that it doesn't is if you look at these three paths, the AB paths, it means that there's a, okay, so the cycle was induced. There's a way to make that cycle induced. So the only way that this is not a theta is that in the center path, there's an edge there's a vertex that's adjacent to a vertex on one of the left or right paths. So, well, let's just say there is one, say like Y to W. Well then, first of all, Y can't be adjacent to A or B. It can't be near the ends here, because then you can just like make a shorter path of length 2. Or if the entire thing was length 2, it would have just been a wheel in the first place, because it would have been A, Y, B, and the A, Y would be an edge, Y, B would be an edge. Then the outside cycle would be a cycle, and Y would be the center of a wheel, which is not allowed. So if it's not a wheel, then Y is somewhere in the middle. It's not near the ends. And then you have Y to W. But then like, why doesn't BYW give you a smaller path? Well, then it must be that W and B are adjacent. So this is WB is just the edge. But the same argument holds for A and W. It should just give you, A to Y and to W should just give you a shorter R. But so that means A and W are adjacent. And now if you have a vertex on the left side of AB on the left path there, and it's adjacent to the path as well, then you can make a shorter R with that as well. You just take that vertex, go to the path, go to Y, and then go to W. And that's shorter because it only takes two edges, and you know that Y and the other vertex is not adjacent to A or B. So just by some counting, you can show that it's shorter. So there's no such thing because, well, we should have picked the shorter one then if it existed. So that means that this cycle, it's a cycle, it's induced. There's no chords. Well, then this just, W is adjacent to Y, is adjacent to A, is adjacent to B, it's adjacent to three vertices on a cycle. So that means it's a wheel. So that gives you the contradiction there, I guess. So G has no K4 minor because of this. Okay, what about the other minor that you would get from outer planar, which is K23? Well, you just look at a subdivision of K23. And then you take H, that's the shortest one. And then all three of these paths, if you look at the internal path themselves, they're induced. If they weren't induced, you should have picked a shorter one. And then the only thing that would prevent this from being a theta or closed theta, which means an edge from U to V, is an edge from one of these paths to another path. But it gives you K4, which we already showed that doesn't exist. So that means that there's no this structure. So there's no K23 subdivision. So there's no K23 minor. And so I should have probably put these slides first. But, I mean, the ordering wasn't optimal. In basically the first paper on outer planar, they showed that the characterization outer planar contains no K23 minor and no K4 minor. So since we just showed that the graph G has no K23 minor and no K4 minor, it's outer planar. And in that same first paper, they showed that every two connected outer planar graph is Hamiltonian. So G is two connected outer planars, so it's Hamiltonian. So that means that we get the contradiction required. It's Hamiltonian if it doesn't contain those three classes of those three classes of subgraphs that we want to exclude: the theta, the closed theta, and the triangle free wheel. Okay, so here's a reason perhaps why the triangle free case is not as exciting, because we had to exclude like triangle free wheels here, but we can sort of just exclude all wheels. So this is so we've been working on. I mean, we already wrote up some draft about this, but it's not done yet. But we're pretty sure that this is basically what the case is for wheel free. So if you have like if you have wheel free, then you're obviously triangle free wheel free. Wait, yeah, if you're wheel free, you're triangle free wheel free. So the idea is, what are the HC obstructions of wheel free graphs? What are all of them? And we think it's just these four. Okay, these four and the closed versions of these four. So in the theta, we talked about earlier that if you take the two ends of theta and you connect them with an edge, that doesn't help you at all, because the argument didn't, like, it doesn't help you to have the edge there. It's the same for the two triangles connected by paths. Okay, yeah, so if you have two triangles connected by paths, you have the same problem. Okay, suppose these paths are more than length one, they're long paths. Any potential Hamiltonian cycle will have to contain the entire paths. So if you add in that one edge between the ends of the path, it's not going to help you obtain a Hamiltonian cycle. I mean, it's not exactly these configurations, but it's related to these. So this will probably appear later. So that's it. This is the idea of what we're trying to accomplish. That we're trying to find all of the HC obstructions of two connected graphs in general. That's really hard, so we just did it for two classes instead. Thanks for listening to my talk.
Awesome. Thank you so much, Zishen. Let's do a round of applause if everyone could please unmute, and then I'll count to 3 and then we'll clap. 1, 2, 3. Awesome, thanks. Does anyone have any questions?
Yeah, so most of your examples have vertices of degree 2, and the ones that don't would have vertices of low degree anyway. So if I was looking at AC minimal things, do you know how to prove like something like the minimum has vertices of low degree anyway?
Has vertices of low degree anywhere? What do you mean?
Well, I mean, they do. I mean, they, like,
yeah.
Or low, like the average degree is small, or like in general. So basically, I'm wondering whether you can prove either results that say that the class gets really messy, or if there's something nice about the things. And the average degree looks like it's really small.
Yeah, I don't know. Like we looked at some examples of HC obstructions, and it does seem like a lot of times there's degree 2 vertices. But maybe it's just because when we tried to like prove that the constructions are HC obstructions, it's really helpful to have degree 2 vertices. I don't. There might be like obstructions that are really complicated. Like we only were able to classify for certain classes of graphs, right? So maybe for two connected, it's complicated.
Yeah, it'd be really interesting if there were classes where the minimum degree was large.
That's a good point.
All right, are there any other questions? All right, maybe we'll end the recording there and then have some more time for informal discussion. Thanks again.